So section 4.5 is where we put it all together. We start using all the tricks you've learned, not only in this course, but in college algebra, to help graph a function. Now, the first thing you should always be doing when you're looking at a function is considering its domain. Where is the function defined? You don't want to bother trying to graph points like minimums or maximums if it's a point outside the domain. You're not going to get anything outside there. One of the things that's not as critical as it used to be, although it's still good to know, is anything about the symmetry. So is it an even function? Now, if you've got an even function, then the graph is symmetric with respect to the y-axis, so that the left of the y-axis and the right of the y-axis are mirror images of each other. So your even functions would include like the absolute value of x, y equals a cosine of x, or x to some even power. Those would all be examples of even functions. Odd functions, odd symmetry is harder to use and see. It's sometimes called origin symmetry, but Rational functions, you can use some long division. And then if you did use some long division, you probably get a quotient and remainder, and that could help you out because the quotient is going to be kind of your asymptote in some sense, or maybe it's a direct sense if it's an oblique asymptote. But the long-term behavior of the function is going to be discussed by if the degree of the numerator is less than the degree of the denominator, then y equals 0 is your horizontal asymptote. If the degrees are equal, then you get y equals this line, which is the ratio of the leading coefficients. So there's a lot of things you can look for. Intercepts, vertical asymptotes, increasing and decreasing. So here's where your calculus kicks in. Inflection points, concave up, concave down, all kinds of things come together. Now we're going to focus mostly on the calculus part of it, and we'll start with this one right here. So y equals x to the 4th minus 8x squared plus 8. Now, I guess in keeping with what I just said, I'll start up by reminding you that this is a polynomial. Its domain is everything, negative infinity to infinity. There's no point at which this is going to be undefined. So they're wonderful functions to work with. And you'll see more of that as we continue in this course. There is something else that's worth noting about this. If you take a look at the exponents, they're all even powers. Now, I'm not going to review the algebra for it, but this is an even function. So that means the left-hand side of the graph and the right-hand side of the graph should be mirror images of each other. What else can we do? Well, it's not a rational function, so we're out of luck there. Let's just get busy with the calculus part, finding some derivatives and graphing it. So dy by dx, or y prime as you see fit, that's going to be pretty easy. This is just a polynomial. 4x squared, 4x cubed minus 16x. And let's just immediately set that equal to 0 and solve. And how am I going to do that? Well, probably factor out a 4x. And that's going to leave behind x squared minus 4. And then I can factor that further. 4x times x minus 2 times x plus 2. Whew. The nice thing about this is that I can probably just read off where this is equal to 0. Where does this function equal 0?
0 and 2 and negative 2.
Awesome. Thank you, Marley. 0, 2, and negative 2. Okay. Let's do ourselves a little bit of a chart here. x, y, and y prime, -2, 0, and 2. All right, so the derivative is 0 at all 3 of these points. That's fine. We're going to have to test points in between to find if the sign of the derivative is going to be positive or negative. So let's see if we can't just do that by looking at the derivative. If I was to put in a point, say -3, that'd be negative, negative, and negative. So overall should be negative. That's what I'm getting. You know what? Maybe I shouldn't just rely on kind of a quick look at it. Let's put in the function. Clear this out. 4x cubed minus 16x. Oops, got to exit the exponent. So minus 16x. Now let's go to our table. It should be set up so that independent is set to ask, dependent is set to auto. Table. We'll test values at -3, -1, 1, and 3. Not a huge surprise here. Does match what I expected. Negative, positive, negative, positive. So we're good there. Somebody explain to me what I learned by doing all these test points. What does that tell me about the function?
How it's increasing and decreasing.
Yep, thanks, Cole. So decreasing, increasing, decreasing, increasing. Excellent. Thank you, Cole. Someone else tell me what kind of a point -2 has to be.
Inflection point?
Relative min.
Oh.
Relative min. Yeah, relative min. Because the function is going down and then starts going up. So it has to be a relative min. And then 0 has to be what?
Max.
Relative max. Thank you, AC. And finally, a relative min. Okay, looking good so far. Let's keep going with the second derivative. Now, I don't think I do the second derivative here. I go back over to here to do the second derivative. That's going to give me 12x squared minus 16. So y double prime equals 12x squared minus 16. If I set that equal to 0, that's not going to be some pretty points. That's okay. So it's going to be 16 equals 12x squared. 16 over 12 equals x squared. That's going to simplify to 4/3. And if I take the square root on both sides, I'll end up with plus or minus the square root of 4/3. The square root of 4/3 can be simplified some more. You can take the square root of 4 and get 2, etc. You can clean it all up. I'm not sure that it really matters. WebAssign, I think, is going to be fine with plus or minus square root of 4/3. So let's go there. In case you're curious, though, I think formally in the book, you'd probably see something like this: 2 square roots of 3 over 3. That's probably how they'd write it. Okay. So we'll make a little table like we did with the last one. X, Y, Y double prime. And we have points at negative square root of 4/3 and positive square root of 4/3. So when I read your notes after your exam, I'd like to see tables like this. It helps me out. I like the way it organizes information too. 0, 0. Now this is y double prime equals 12 minus 12x squared minus 16. I think I can do this one without necessarily putting it in my calculator. So a number like -5 squared is 25 times 12 is 300 minus 16. I think that's positive, negative, positive. What is that telling me? Somebody I haven't heard from yet today. Wasn't a chance to say something. Kennedy, what's this telling me about the function that its second derivative is positive here?
That the graph is going up.
In what way? Concave up, concave down? So would this be concave up or concave down? Something happened to your mic there. So let me just help out. It'd be concave up, concave down, concave up. So thank you. And I think okay, I got you back. I don't know what happened with the Zoom, but oops. Share screen. Okay. Like I said, I got you back. So think we were right here. I was plugging in some values like -2. I don't know. You tell me, at what point did I lose connection?
We were talking about what the plus and minuses on either side of square root 4/3 tell us.
Oh, okay. That's right. All right. Thank you. I didn't know at what point, because I thought Kennedy's mic just went out for a second. So let me go back here. Let's see. So I think Kennedy was telling us that the plus here reflects that this is concave up, then concave down, then concave up again. So thank you, Kennedy. That makes these inflection points. And let's put that together with the graph. See if we can't figure out some things there. So I know that this is an inflection point. This one's an inflection point. And then let's see what else I got. And that's a relative min. This is a relative min. And then I got a relative max. And all that seems to make sense. Now, there's nothing wrong at all with looking at the graph on your calculator or on Desmos or on some other thing, but it should match. So what's going to go on here is that the graph is going to come down to this minimum. So it's going to come here. And right here, the function is going to change concavity. It's changing from a concave up shape to a concave down shape. So let's see if I got a different color pen I can use. Yeah. So it's going to be concave down here until it gets back to the other inflection point. So Just like that, concave down. And then what? Then this process repeats itself. Keep in mind that the function is a mirror image of itself. So it's going to be concave up like that. Beautiful. Beautiful graph, uses all the information we picked up from there. Okay. We're good with that first one? All right. Let's try some more here in the same section. Let's move over to problem number 10. Now, I'm sure that most of you don't have your book open, so that's okay. Let me tell you what problem 10 is. Problem 10. We're going to have y equals x squared plus 5x over 25 minus x squared. And then let me helpfully give you the first and second derivatives. The first derivative is 5 over x minus 5 squared. Now, if I gave you the first derivative like this, you could be clever in getting the second derivative. How could you help yourself in getting the second derivative? What would you have to do to get the second derivative?
Quotient rule.
Yeah, quotient rule. Now, I can't really see on the Zoom, but I'll ask this question anyways. Raise your hand if you like using the quotient rule. All right, I don't see any hands. No one likes using the quotient rule. It's a pain. So what you could do is write that as 5 times x minus 5 to the negative second power, like that, and it's going to be easier to differentiate. So y double prime would be negative 10 x minus 5 to the negative third power, which is negative 10 over x minus 5 cubed. So a lot nicer than the quotient rule. Wouldn't you agree, AC?
I agree.
Okay, so nice. So we've got the function, the first and second derivatives. That's great. Let's see what we can figure out about the function before we start graphing it. So in looking at the function, let me rewrite it like this: x squared plus 5x over negative x squared plus 25. And there's something I wanted to do by rearranging it like that, is I wanted to highlight the fact that these things have the same coefficient. Now, why is that important? Or it's not same coefficient, same degree in the numerator and denominator. Why is that important? Let me help out. If we go back to our handout, kind of at the top, where'd that go? Where did it go? Slant this. There we go. If the degree of the numerator and the degree of the denominator are equal, so this is case B here, right here. If they're equal, then you get a horizontal asymptote, which is really just a ratio of the leading coefficients. So what does that mean for us? That means that the leading coefficient in the numerator is 1, and the leading coefficient in the denominator is -1, that we get y equals 1 over -1, or basically just -1. That's going to be an asymptote for the graph. It's going to be a horizontal asymptote. Horizontal asymptote. That's an important feature for this graph. You should know that one. Now, what else can I figure out about this graph? Well, there's other asymptotes that you can get as well. We got the horizontal asymptote, but how about some vertical asymptotes? Where are you going to get your vertical asymptotes?
When x equals 0?
When x equals 0 would tell you where the graph crosses the y-axis. So, I mean, setting x equals 0 is a good thing to do. So thank you.
25 minus x squared equals to 0.
Yeah, where the denominator equals 0, that's where you could get a vertical asymptote. So let's see about finding those points. Go. Now I'm going to work with both the numerator and denominator to factor them. So going up here, this is going to factor as x times x plus 5. And this denominator, let's see which one do I want to do it. I can factor from here. It'd be 5 minus x times 5 plus x. Now that's interesting. Does it matter if I do 5 plus x or x plus 5? Aren't those the same? In fact, it looks like this term in the numerator and denominator is kind of the same. So am I going to get a vertical asymptote there? Does anyone know what feature of a graph I am going to get here? The graph's not defined here, but I don't get a vertical asymptote. Let's actually start looking at the graph a little bit. So let's see here. Let me see if I can't find you guys a Desmos link. I know, shocker, Desmos. Okay, so let me give you a link here. I'll put it in the chat. You might find this one fun to open up. And I'm hoping it opens up to something like what I've got here. Is that what you're seeing? Someone want to tell me? So the first thing we need to do is we need to figure out where the asymptotes are on this graph. But I like a little feedback. Are you guys getting to this? I mean, it's just a blank graph, but you should have this stuff on the left.
Yeah.
Yeah.
Okay, thank you. So I wanted to figure out where the asymptotes are, and we found a horizontal asymptote, but there's also going to be another asymptote for this graph. Now, as long as you're not at x equal -5, you can get rid of these. And this is roughly equivalent to x over 5 minus x. Where is this going to have problems?
+5.
Yeah, thank you. So it's going to have a vertical asymptote at x equal 5. Beautiful. Now, what's happening with this function at x equal -5? Well, well, you're going to get a hole in the graph. You're not going to get a vertical asymptote. And to figure out where you're going to get that hole in that graph, you could take a look at the limit as x approaches -5 of this. So the limit as x approaches -5 of x over 5 minus x, that's going to be what? -5 over 5 minus -5 gives you -1/2. Let me simplify it. So we should find a hole at -5 and -1/2. Let's see a few of these things. So if you click the circle to the left here of that top line, it should sketch in your vertical asymptote and your horizontal asymptote. If you click the second one, it'll tell you the point of the hole in the graph. And in fact, I think somebody made a suggestion of setting x equal to 0, right? If you set x equal to 0, you're going to get the y-intercept. So if you go all the way back to setting x equal to 0, where's the y-intercept? Where's that going to cross the y-axis? If I set x equals 0 in the function, not in any of its derivatives. Someone want to do that for me? 0 squared plus 5 times 0 divided by 25. It's going to be 0, right? So that's going to be a point on our graph as well. Time to do some calculus. We've got our first and second derivatives. The thing about the testing here is that you've got to be a little bit careful. The domain of this function was, we didn't really determine it, but for the domain of the function, you can't put in x equal 5, nor can you put in x equal -5. So our domain is everything but 5 and -5. So -infinity to -5, and I'll write it the WebAssign way with commas, -5 to 5, comma, 5 to infinity. Those are, that's our domain. You're just working around -5 and 5. Got to avoid those points. Because that's where the denominator is going to be 0 and the function is going to be undefined. But there's still points that you got to test around. So x, y, and y prime. So there's our derivative. Could this equal 0 any place? It's only going to equal 0 where the numerator equals 0. And since 5 can't equal 0, it's not going to equal 0. It can be undefined at x equal 5. So at x equal 5, it's undefined. Of course, that point is not even in the domain. That's okay. The important thing is that you need to test for change of signs on either side of that. So I need a test point to the left of 5 and to the right of 5. Y prime equals 5 over x minus 5 squared. I'm not going to bother putting this one into a calculator. I think we can kind of anticipate the sign here. Let's just choose something like 0. 0 minus 5 is -5 squared is 25. But the numerator is positive and so is the denominator. So this is going to be positive. If I choose a value like 6, 6 minus 5 is positive, squared is still positive, divided by into 5 is still positive. In other words, the function is doing what? To the left and to the right of 5.
Increasing.
It's increasing. So let's take a look back at our graph. Where is the function increasing? Well, like everywhere. But let's do the, you know what? Let's do the concavity first, and then we'll reveal the whole graph. So for the last part here, we're going to look at the concavity. So y double prime equals -10 over x minus 5 cubed. I'm going to do a little testing here as well. X, y, y prime, y double prime. The only place that this can change signs is at x equal 5, where the denominator can go from positive to negative or vice versa. We just need to figure out what's happening there. Now I want you to do this. See if you can do it in your head. If you trust yourself, if not, then take out your graphing calculator or something else. But do a little Gedanken experiment like Einstein used to do, thought experiments. Plug in a 0 here. Now, you don't have to come up with the exact number, but 0 minus 5 is going to be negative. If I cube something which is negative, do I get something negative or positive?
Negative.
Yeah, you get a negative. And a negative divided by a negative is positive. So I expect something to the left of 5. I expect the graph to have what kind of shape? Concave up. How about to the right of 5? Say choose 6. 6 will work out pretty good because 6 minus 5 is 1. Cubed is still 1. -10 divided by 1 is negative. So concave down.
Okay, I've got to ask. In all of math, do they use concave up and concave down and just ignore that the word convex is a thing? Or is that just us?
No. The convex does come up in math. It's actually a very important idea in topology. Convex set. I think convex sets, if I remember, are simply connected, meaning you can draw a line from one point to the next and still remain within the set. So,
okay, because I've been terribly confused with the concave up, concave down.
Yeah, I strictly just use concave up and concave down. All right, convex. Okay. I know that you make convex lenses. Yeah, I'm not sure. Yeah, I haven't thought about convex in a while, so I don't want to venture out into that territory right now. It's a good question though. Yeah. You're making me think about convex now. it's distracting me, but it's interesting stuff. Convex sets, yeah, that's a good subject in topology. You'll get there if you stick with that long enough. But let's stick back with this though. Does that make 5 an inflection point? The answer is no. 5 is not in the domain. It's not an inflection point. So if we actually look at the graph now, and we can kind of light these things up now, where's the function concave up? Oh, okay, yeah, to the left of this. Where's the concave down? Oh, to the right of that. And you can scroll and zoom out a little bit, maybe reposition this. It's fine. Where is the function increasing? Everywhere, right? From negative infinity to infinity. We saw that. And when you look at the graph, it is increasing everywhere. Let me get rid of the asymptotes here real quick. But here's just the graph. As you move from left to right, it's increasing everywhere. It just has this brief, weird little pause at x equal 5 because you have a vertical asymptote there. All right, that one worked out pretty nice. Any other questions or thoughts there other than convex and concave? So, okay. Let's see. Let me continue. I want to do what should be on your handout is problem number 30. And 30 has some more of that factorization I promised you from section 4.3. So let's cut over to this. Y equals x to the 5/3 minus 5x to the 2/3. So the first thing we should look at, and I'm not always good about doing this myself, but really you should look at the domain of this function. Now, if you were to rewrite this as, say, the cube root of x to the 5th minus 5 times the cube root of x squared, you're not going to have any problems with negative numbers underneath a cube root. So we're okay. There's no problems with zeros in the denominator, that kind of thing. So the domain is everything. So the domain is going to be negative infinity to infinity. All right, well, what else? Now, I don't see that this is necessarily going to be an even function or an odd function. So let's just move on and start calculating some derivatives. Now, there's a look at the function itself. Let me maybe try and improve the graph a little bit. There we go, stretch it out. All right, so you can tell some of the things by looking at the graph, but not everything. One of the things I want you to get out of this example is how to factor some of these derivatives. This is like our problem from section 4.3 in one sense. So y prime is going to be 5/3 x to the 2/3 minus 10/3 x to the negative 1/3. And while we're at it, we might as well calculate y double prime. 2/3 times 5/3 is going to be 10/9 x to the negative 1/3. Negative times negative is going to be positive. This time I'll get 10/9 and x to the negative 4/3, just subtracting 1 from the exponent each time. The challenging part is going to be finding where this is equal to 0 or does not exist. And that's the part that I'm going to help you out with. That's the part that's going to require a little fancy footwork in terms of the factorization. So let's start by finding where the first derivative is 0 or doesn't exist. Let me rewrite that over here. Y prime is going to be 5/3 x to the 2/3 minus 10/3 x to the negative 1/3. Now I mentioned this trick a while ago, but let me bring it back here. To factor this, I would factor out the largest negative exponent that you can. In this case, it's going to be an x to the negative 1/3. So let me just do it this way. Let's put x to the negative 1/3 out in front. What else can I factor out? Well, there's a common denominator of a 1/3 here and a 5. So a 5/3 x to the negative 1/3, that's what's going to get factored out from both of these. Now, when I factor something out, I have to divide each of those terms by that factor. So each of these terms is going to get divided by 5/3 x to the negative 1/3. 5/3 x to the negative 1/3. And that's going to divide into these terms. 5/3 x to the 2/3 minus 10/3 x to the negative 1/3. Now, later on, maybe you can get really good at factoring these things out. You won't have to do this step. That's fine. I do want to see it factored. You do need to factor it. But all we're doing is we're taking out that factor, that GCF, and now we're going to simplify. So it's going to put a 5/3 x to the -1/3 here. Let's see what's left inside. I'm going to start with the easier part here. That term and that term cancel out completely. So you're left with 10/3 divided by 5/3. Now, I'm not sure how good you are at doing that in your head, so let me help out. When you divide a fraction by a fraction, you end up inverting and multiplying. So it's going to be 10/3 times 3/5. What's that going to leave me with?
2.
2, yeah. So I'll have a -2 here. Now let's work with here. And again, you're going to get some nice cancellation here. This time, it's going to be the 5/3 that cancel. But with this stuff, now you're looking at x to the 2/3 minus x to the -1/3. And if you're careful with that double negative, 2/3 minus -1/3, you realize it's 2/3 plus 1/3, leaving me with just x to the first power. Last but not least, I've got a negative exponent here. I'm going to put that in the denominator along with the 3. The 5 I'll leave up in the numerator. So overall, it's going to look like 5 times x minus 2 over 3x to the 1/3 power. Okay. So that's your y prime.
I've got a quick question.
Yeah, Cole, please.
I noticed when we factor sometimes where you use brackets instead of parentheses. Is there a reason for that?
Just visual. Just
Okay.
visual. I just want you to be able to see, one versus the other.
Okay, because I noticed some of the solutions on WebAssign, they do the same thing, so I wasn't sure if there was a reason for it.
Yeah, it's just a visual thing. Yeah, I mean, there's mathematically, they're equivalent. They mean the same thing. A lot of times I'll use them when things get nested and you have multiple things going on. Here, I just did it. Yeah, I don't even think about it anymore. So thanks for the question, though. Now, the critical points are going to be where this is equal to 0 or doesn't exist. The nice thing about this factorization is you can read that off. Critical points, where does this actually equal 0? That's going to be where the numerator is 0, right? So where's that? Anyone?
+2.
At 2. And where the denominator equals 0, which is at 0. So critical points at 2 and 0. And you can see that, right? You can see that from the graph. Critical point at 0. Oh, yeah, the derivative doesn't exist here, right? Because you got a corner point. You're not going to get a derivative at a corner point. And guess what? You got a minimum here at 2. Cool. Now, let's see if we can't figure out some things about the second derivative. I'm going to give you a chance to work on the second derivative. I'll get you a little ways. I want you to practice that factorization, factoring out that negative exponent term. So we already calculated the second derivative was y double prime was 10/9 x to the -1/3 plus 10/9 x to the -4/3. So if I'm going to factor this, I want to factor out the largest negative exponent term that I can. Now that's my common term here. My common factor is going to include a 10/9 x to what power?
-4/3.
You want the largest negative exponent possible, so -4/3. So let's do this again. You know, and look, if you can do this in your head, that's great. Really, you're going to be adding 4/3 to both these exponents. So if you can do it in your head, that's awesome. I'll show it for those of you who want a little bit more detail. So that's going to be, let's see, everything's going to get divided by this term out in front. And let me give you a second or two to work on that. So this has got a plus between these things. So let me put a plus here. This term that I factored out, 10/9 x to the -4/3 goes in both denominators. In the numerator, I've got 10/9 x to the -1/3, and then 10/9 x to the -4/3. So unlike the last one, we're going to get a little bit more cancellation in a nice meaningful way. And that meaningful way is the 10/9 here and here are going to cancel out altogether. And then what else cancels out? Well, that whole thing cancels out. Now, it doesn't cancel into oblivion. Really, you're dividing something by itself. And when you divide something by itself, you get 1. And almost the same thing happens over here. Are we good with this right term before I work on the left term?
Yeah.
Thanks, Matt. Now on the left term, the 10/9 cancel, but here you've got to take and divide this by this. And when that happens, you subtract exponents. So -1/3 minus -4/3. Now the thing about these problems that's going to always work out for you is that you should end up with a nice integer exponent. In this case, a minus becomes a plus. What's -1/3 plus 4/3?
1.
1.
1. Excellent. So overall, what you should have is this times x plus 1. So let's put that together. So 10/9 x to the -4/3 times x plus 1. And now the 10 is going to stay in the numerator. This term goes down in the denominator along with the 9. So it's going to be 10 times x plus 1 over 9x to the 4/3. But you got to get that factorization right in order to figure out things about its concavity. It's just going to be tough. So f double prime of x equals 0 at x equal -1, and f double prime of x does not exist at x equals 0. Yeah. I think I can tell what's going to happen at -1. You're going to have an inflection point. I think it's going to change concavity there. But we'll decide that looking at the graph. The big important thing to get out of this example was the factorization. So are we okay with the factorization here? You've got to be able to clean up these derivatives in order to figure out where something is equal to 0 or does not exist, that kind of thing. It's just not something you can do easily in another way. All right, let's match this up with some of the things that we see in the graph. I'm not going to take the time to do a little table of increasing and decreasing, that kind of stuff on this one. Let's just look at the examples. or look at the graph. So we see that we got an undefined derivative here at 0. And the function is concave up to the right of 0. But to the left of 0, it's kind of tough to tell, right? Left of 0, don't know. But what we see from the derivatives at -1, you have a change in concavity. And it's just, even with the calculus, it's just tough to see if it's concave up or concave down. Maybe we should actually take the time to do a little bit of a test here. So let's just look at this, the derivative, the second derivative, just write concave up and concave down. I'm just curious. So x, f double prime, -1, and 0. So kind of a modest little table here. Let's see if we can't figure some things out. Here, here. Zero. This backwards E with a slash through it means does not exist. It's because I ran out of room to write that. We're going to be testing the second derivative, which is going to be f double prime of x is 10 times x plus 1 over 9x to the 4/3. Let's take a point like -2. If I plug in -2, the numerator is going to be negative, and the denominator is going to be positive. So I think that's going to be negative. Between here, it's going to be positive and positive again. So you should have concave down, concave up, and concave up again. Hard to spot. I mean, you just can't tell without the calculus. It'd probably take a little bit more time on my part. And even then, I don't know if I could do it to make this graph actually look like it's concave down starting right there. So let's actually put a point there on that graph. I'll do it this way. F of x and -1 comma f of -1. There you go. Well, I would not get that that changes concavity here without the calculus. So, all right. Any comments or thoughts on that one? The big piece to get out of this is factoring out those negative exponents like that and cleaning up your derivative. Because once it's here, it's easy to see where the inflection points are. But without that,
question.
Yeah, Aiden, please.
How did you get it doesn't exist at 0?
Oh, the denominator would be 0, so the whole thing would be undefined, right? You can't divide by 0.
Okay, gotcha.
Appreciate that. Thank you. Anything else that you're curious about? All right. So I like to do this last kind of problem, especially in class. I don't know as I'll be able to do something exactly like this through WebAssign, but you never know. So we'll call this one a mystery function. Mystery function. And let me tell you a few things about our mystery function. Call it mystery function 1. And the first thing I'm going to start with is that f of x is an odd function. Let me remind you what an odd function means. An odd function means that you've got what's called origin symmetry. So it's not really easy to see. I mean, an even function is wonderful because it's just symmetric with respect to the y-axis. An odd function means that when you draw a line through the origin, that it's going to intersect the graph at points that are on opposite sides of the origin. So I've got a point here at 3.162 and 3.162. I got another point at the same but opposite side on the other side of the graph, on the other side of the origin. So no matter where I rotate this, that same kind of phenomenon is going to happen. So if I click again, I've got up here and another symmetric point on the opposite side of the origin over here. It's not as visually striking as a nice even graph. Nice even graph like y equals x to the fourth minus, say, 4x squared. Beautiful, nice and symmetric. You can see and appreciate that easier. Odd symmetry, not as easy to appreciate. All right, so the function's an odd function. That's one thing I'll tell you about it. Its domain is from -2 to 2. F prime of x equals 0 at plus or minus the square root of 2. F prime of x is undefined or does not exist at 2 and -2. Let's see how I want to write that. Let's do it this way. At x equals plus or minus 2. So those are a couple things to know about it. And then I can give you a little bit more information here. Some of my little tables. And see if you can't fill in some things here. X, F, F prime, and -√2, √2, X, F, F double prime, and 0. So here's some tables. And let me tell you that the sign of the derivative to the left here is negative, positive, negative, positive, and negative here. Now I want you to think about what this is telling you about the function. See if you can't answer a few questions that I'm going to give you on the link that I'm going to send out. So. Okay, so the idea was to use this information to make predictions about the function. Now, the first one is probably the toughest one, I would think, especially if you're not used to odd functions. But the function has a point right here at 2 and 0. If it's an odd function, then it has to have a symmetric point on the other side of the origin, which would be right over here at -2 and 0. So, okay, kind of a cheap one to start with. But where are the critical points? What tells you that something's a critical point? What information do you have that says something's a critical point? What tells you that it's a critical point?
F prime is 0.
F prime is 0, okay. And what else?
The sign changes.
Or the derivative doesn't exist. So if you're looking for the critical points, how many of them should there be? 4, right? 2 here and 2 more here. So if you light those up, you know where the x coordinates are, the y coordinates, you'd have to know the function, but I didn't give you that. But there you go. So at √2 and -√2. And again, notice that they're on opposite sides of the origin. Where is the function increasing? What's going to tell me that the function's increasing?
Plus sign.
Yeah, the plus sign. So the first derivative is positive. That's going to happen between -√2 and 2. So you can play connect the dots between a couple of those points. So this point to this point, the function should be increasing. Bam, looking good. Let's make this a little darker. If you click the tool icon and click the capital A, makes it a little darker, a little easier to see here. Where's the function decreasing? Well, it's got to be decreasing everywhere else. So that's kind of easy right there. Does the function have any inflection points? If so, what are its coordinates? So let's look back here. How could I tell that the function has an inflection point? What happens at an inflection point? What information would help me locate an inflection point?
Sign change.
Sign change in the second derivative. So this is an inflection point. 0 is an inflection point. The shape goes from concave up to concave down, right at 0. So does it have a inflection point? If so, what are the coordinates? 0, 0. That's your inflection point. Now, if you're struggling with the idea of the fact that this is an odd function, you can use this down here, kind of spin this graph a little bit. Let's just turn it on first. And notice that the origin is kind of a midpoint for places where the line intersects the graph. Here and here, here and here. You have symmetric points located on either side of the origin. It's not a huge thing, but later on in chapter 5 and 6, there is a spot where it's very, very, very convenient to notice that something's an odd function. Any wrap-ups on this? Any other comments, thoughts, or anything else? All right, I think that's it for this section. So we'll stop here.